Nice to meet you to this new episode of Wigbit. Yeah, on the kitchen table is the ATMega328, what we would like to talk about, and a wish from my friend Paul in Canada. He would like to learn the assembly code for this microcontroller. And I got this pack long time ago. I ordered 10 pieces of that, and this is a small developer board for a microcontroller. And here you can see, here we have a text tool socket. This is a socket where you can clamp in a hardware like this. We must say we have two things to understand. There are general types, two types or more types. I don't know how much processors or whatever exist. And we get this. Look at the mark. Here is the mark. There is a mark on it. Here we are. You can see that here. Here is a mark, here's number 1, yeah, and number 1 is here on this texture socket here on this side. I know that because I have a lot of them, and now we fix it. It cannot fall off. It's connected now through the pins. If you release it, you can lift up, and if you hold it and fix it, then it cannot fall out and have contact to this little things here, to these pins. Yeah, what we should say is a microcontroller is a little controller that it's not a processor, it's a processor also with external interfaces like these pins and ports, and can work autark. That means with no external hardware. It can work also to control a LED or transistor and so on, external. The RAM is inside, and the flash memory for the program is also inside this part. Yeah. Here we have also a possibility to have a connector to program it with an interface, and I would like to show you this later. What we can say, important things are the power supply. The power supply is here, I think so, from 2.4 volts to 5 volts or so. And also important, you need a clock. And here we have a little crystal with 8 megahertz. I would like to show you this here. 8 megahertz, you can see that. The 8, yeah, no, you can see it here. Now look, it's 8. It's 8 megahertz. We making the calculation how is a cycle, how needs a cycle, and so on. And also we have here a reset. The first interrupt is a reset. Then the processor starts on a special point. In this case, at address is the program counter at address 0. It starts. Other processors like the 5602. Not controller, this is a controller, yeah? Starts, for example, the processor 6502 starts on a higher address, and this starts at 0. We will show that. And here we have the board pins. Also these yellow things, they are out. You have the pins for the board. We have port D, I think, port D0, port D1, port D2, and so on, port D7. And here we have port B0 till 7 and port C0 till 6. It's one lost. Power switch, yeah. And here we have also the supply. The energy supply is also important, yes. The data sheet we can watch in our computer that I would like to show you during the assembly code that we write first. And now we would like to write first the assembly code. But first I would like to show you how I do this. I make a developer board. It needs a Mr. Brush. A developer board, it's here. And we have also here interesting things on it. The controller and also a 4-line LCD display and a 2-line LCD display. You can see that here. It's a 2-line with 2 lines and 16 characters. And a power supply here. Also this breadboard. You can build up any transistors or other hardware what you would like to control with it. Also, this is important, the thing here, the controller with this connector. This is the serial programming interface. ISP, it's called like here, and to connect with the computer and bring in the software. We called it firmware. At the microcontroller we called it firmware, and in a computer we called it software. This is a firmware.
Yes, we use some assembly, and we're doing the assembly ground course, or the starter, or beginner, or whatever, or know-how. I don't know how I would like to call it. We're using for assembly, we're using a text editor, and I using the normal terminal. It's a bash terminal in my Linux system. Only for recording, I must write this 2 times in case of that this code what came out here is incompatible to the Windows code, and we need a Windows code or a DOS memory. I think so. I can store it also in DOS here, but it's for me. I never do that first. Yeah. But now we start at the first line, where is the blinking cursor on the left side, and you see here dot point, and this is wrong. It's not a dot point. This is a dot comma, I read. Very funny. This is a dot comma, and the important thing is this: in assembly the dot comma makes the remark. All those behind here on the right side is a remark. You can see it's a remark. You can write there high remark or lower. It's not important what you are writing here. All this will not seen from the assembly. It's the same as the in C is this or that remark. This is in C, yeah. And then assembly is the dot comma. And here you write the remark behind on the right side. So what I'm doing, I'm writing here the title. It's the ATM328P underline grid.asen. The thing is that we are writing in low characters, and only the information here is sometimes in high. And I say created double point, yes, on the 10th for 23, okay, and the author was me. And here we can also include a list of parameters. They are written before. I'm doing this with a copy in case of that I cannot remember what's inside my Windows and so on, but I'm recorded only on the Linux, because here I can record the audio too. And here we have the very information. I copy it from another window to this window and say this is the important set, but it's on your machine on the other place where you installed it and you generating a project. We show that later. In case of that, we are doing the assembly in the AVR Studio 6 or 7 or so. This is important for the for the controller. So we remark it. Now we're doing a register definement. This is not needed to write this here, but I do this for you, as you can see, or how we can define registers. Inside these controllers are registers from R0 to R15 and R16 to R31. You see, these registers are all 8-bit wide. You see, it's an 8-bit. Yes. It's important that you know what is a bit. For short information, a bit can be 0 or can be 1 or can be high impedance set. Yeah, that's for listening on a bus. You have only a resistor that is going with a 10 kilo ohms to the VCC. But this later. I know it's a lot of things there later, but now we define here the thing. Now we say def and going with the tabulator in, and we say temporary, and we say is R16. What's happened with this? This is the name, what we're writing here, temp, is only a name that we named the R16. So we're writing not to R16 direct, we're writing to temp, and this is a synonym. And this is a temporary data storage. So you can see. Also we do that with the def and say temp 2 is R17. This is the same. And we say def temp 3 is R18. And we say here def counter is, we declare now the things here, and okay, we are doing this. The distances between are not important. You can, this is the blinky counter. We call it blinky counter, and then we're making a definition. Status. We are also making a status register where we got the bits in. And the left bit is called like MSB. Yes, this is MSB. It's the left bit is number 7. Yeah, and the lowest bit is, here we have oh, you see, it's complicated, huh? 6, 5, 5, 4, 3. Oh, there's a bracket. 2, 1, and important number 0. This is the LSB. Lowest significant bit, most significant bit. Here's the MSB. It's the higher. If we're talking about the MSB, it's the higher, and if we're talking about it, it's the lowest. Yeah. These make the orientation. You can see here. And here we say from int 0, we can mark it from interrupt 1, and here we say this is from PC int 20. No, 0. Okay. The other we let free. We use it then later in the following program or following steps, what we're gonna do. So now we would like to have also some things that we said equate board bit def. Yeah. Here we say the bit def. And we're doing this with this, and say this is the bit from, oh no, this is the bit red LED. We say a red LED, we need in future a red LED, and we say this came to, we have port X, and this is a red LED. Okay. Yeah, funny, it's red. And we can send it to some boards. I show you the board B and the board C and the board D we have on this controller. We can switch on and switch off a LED that's outside of the controller. And yeah, these are the bit definitions. We do the same with with the next one color. We say yellow LED. You see, it's a lot of work, and port X, yellow LED. Now it's red. It's yellow, but it's red on my screen. And then we say also green. Oh, there is a R. Green LED is number 2. We say here port X, green LED. This is only the remarker. And we equate bit with white LED. It's number 3. White LED, and the next one is equation. It's the bit blue LED. I think so. They're doing all spectral. Port X, blue LED. And then one important thing is the OSCI bit. This is for us the important thing, to measure outside with an oscilloscope what's happened inside the controller, and that's the this is the port X oscilloscope pin out for measurement. We can see that. Yeah, that's cool. Now we defined the status register, and the status register is here, and we say dot comma status reg. What's happened, which bit is in the status register. We say equal bit from interrupt 0, it's O. And this signal X down interrupt 0, it's signaling. What's an interrupt? An interrupt is if you have a pin like this interrupt 0 pin, and you have there a button, you press this button. This makes an interrupt. If the interrupt is programmed, makes an interrupt in the system, and then the controller is doing the interrupt routine. that we also use in future, and so we defined it yet at the moment. It's not important yet, but we need it then later. Interrupt 1, okay, this is interrupt 1, and then we say it's equal. Oh, there is one wrong. If you type one wrong, it comes to an error from PC interrupt 20. There are fixed interrupts. Yep. And there are not fixed interrupts that you can program it. Two interrupts are fixed, the interrupt 0 and the interrupt 1. The external are fixed, and there are other external exist that you can program free on the pins, and here is the interrupt 20, what we also programmed in future. Then we define something numbers and names, and we say equal. Oh, hey, come on, today is a day. Null, we defined null, it's null. X00. What does it mean? This is a hex number. Hex number 40. Yeah. It means only hex number 40. And then we defined 1. You can see this is the hex number for hex number 41. Okay, and we say 8. It's 8. Hex number 4 8. Okay, and we say FF, and this is the hex number for FF, hex number for 255. Yeah, this is, yep, you can see on the hex. In our case, we put it in the middle, and now we are also programming a compare mask, compare and mask. Compare and mask. I don't know what has happened with this. Equal and sequence, and sequence is this is interest. Trace stop. This is not that program. Compare and mask, but we let that be here. Here comes the bit masks. Bit mask. Then what's the next? This is only a remarker and a whole other shifter. No, we don't know. We say now the port definitions. We say now the port defs. Port defs first is the port B. The port B equation. Init port B is, and now we doing the port B. Is it important or not so important? We say the port B is the we have that here on the OSCI is 5. Okay, bit OSCI is 5. We use the board B as a 7, 6, 5, 7, 6, 5, 4, 3, 2, 1, 0. Yeah, you can see these are 1, 2, 3, 4, 5, 6, 7, 8 pins. This is the LSB and this is the bit number 7. Yeah, and B means this is bit. This is with the bit binary. We are doing this also information for and commas in between, and then we are writing here is number 7 and this number 6 and number 5, and number 5 is the bit OSCI. This is for our output. This defines what is on the board and which bit is which bit. We put here a high out. Yeah, the board B is here on number 5, a high. Yeah, and we also need to know that there is a data direction register. This initialization it in the data direction register for board B, and this must be also, that means out. This means in, out, in, is switched to in. Yeah, you can see this is switched to in and this is switched to out. That means this is hard high on bit number 5. It is hard high, and we are going here and making a copy of that. I hope so. It's not copy, and we fill it in. You can see it. That means out. Yeah, it's an outboard. Yeah. And with the other boards we do the same, but I get a copy from the other boards in case of that we don't write this 1000 times. You must write it, but I don't write it. And we must insert it here. What's happened with it now? It's very complicated. It's oh, there we have the OSCI pin out. Okay. We defined the OSCI pin. Okay, here we defined it. And also the LED. The LEDs will be also defined and here on pin number 5. Okay, that means we clear that to 0. That means no out, and no high. What we're gonna do is we would like to show what's happened in this. Now we go into the next step, and the next step is to initialize the timer. A timer is a clock that you can program in the speed of the cycles or in other speeds. And we are able to know, we would like to say the timer 2 is on page number 116. And the register TCCR2A, or something special register, to control the time is on page number 122. So it's very easy to find out where it is, and I called it Team 2 VGM21. So the register name is, yeah, and this we are defining in a bit 7, 6, 5, 4, 3, 2, 1, 0. Okay, 2, 4, 6, 8. Yeah, that's correct. That's correct. And this is the TCCR2A register would be loaded with inside the VGM22 is the 1 bit. It's 1. Yeah. We also have here the registers. What is happened here, and there are registers like this. Make a copy here. I don't mind first. This is inside this TCCR2A on page number 127, and we go also to the TCCR2B on page number 130, and here we control the timer and so on. And here is a equal Team2 underline stop. This is a command, and this will stop the timer, and it's written for itself. We stop the timer, and we have also a compare Team2 CTC underline CS1024. It's 0B00000111. Very funny for you, huh? It's complicated now because this is a control word for the. It's not a control word. It's a command that the registers are aligning there inside this TCCR2B register. These are control registers, and we have the bits here. What's happened in these control registers, and also we're doing another time too. CS256. This made the preselector for the counter. I would like to tell you now what it is. The preselector is you can run the counter by the clock, yes, and you can divide it also by 256. Now we make a small example. What's happened in the next line, and here we have the OCR2A on page number 131. We need 10 milliseconds at the clock speed at 8 megahertz. 8 megahertz is the clock is 1 divided by 8 megahertz is 0.000 seconds, or further 125 nanoseconds is one cycle. That you can understand it. And now we say this is equal we have the problem that we say, I know that now, we program the prescaler to 1028. In case of what? In case of that doesn't work so fast. Yep. X question mark, and now we say the following. We have 10 milliseconds. 10 milliseconds. This is our interrupt speed. What we need from the timer 2. But we must know 10 milliseconds divided by 125 nanoseconds. It's like this. If you would like to read it in a long number, yeah, divided by is what? That's crazy. I must put it in my calculator. It's 80,000. It's 80,000, and we divide this by 2024. It was divided by 2024. It's 78.25 times. That means it is it is 78. Okay, 78 times, and this is in hex. How much? This is in hex. This is dates to hex. It's 4E. Oh. We got it here. It's 4E. Okay, we're doing the calculation back, and we said 78 times multiply 125 nanoseconds is 78 multiply 125 nanoseconds is it's a long number. It's 0.12312975 seconds. This is 9.75 microseconds. Oh, what not a microseconds. And this multiply 1024 is the prescaler. Multiply 1024, it's 0.009984 seconds. It's around 10 milliseconds. It's 9.984 milliseconds. Yes, and not 10. Yeah, you understand? If we divide it by 2000, if we divide the clock, the 8 megahertz by 2024, yeah, then we come to this result. Yeah. So the next step is we going to the timer mask interrupt, and this is TIMSC2 at page number 132. We also talking about the pages. This is no problem. We got the equation TIM2, and we say OC interrupt enable to A is we have that word here, 0B. I'm sorry, we must also insert this here for E. Yeah. This is our timer for the 10 milliseconds, and we must doing this 0 0 0 0 0 0 1 2. Okay, this is Timsk. Timsk 2, OC interrupt enabled to be bit number 2, yes, in the register, and OCEA, all is register orientated in the controller, and we there have control register TEOA 2, it's number 0. There you can read it at page number 3. Also start the counter, and we say start counter team 2 count. I think it's an initialization. The timer timer 2 is 8-bit. Yeah, the timer 2 is 8-bit. We have also a 16-bit timer here, but we don't use that. We use the 8-bit timer. And also we would like to enable one special function in the thing. This is the sleep. Sleep means we sleep the whole time, and the machine idle at page number 33. SMCR is the register that's called like, and I show you this here. This is equal idle mode enable. Idle mode enable is 0B 1 2 3 4 5 6 7 1. Okay, it's 1, and this enables the sleep. Sleep enabler in SMCR, and there is 7. These bits are empty. 6, 5. The bits with the minus are empty, and 4. And now are the control bits. This is SM2. It's bit number 3. Please read in the page what's happened with this. I show you the page now after this video, and we're doing this in one part. It's a long video, I think so. And we have the SM1, and this is on the pin number 2, and we have SM0 on pin number 1, and we have the SE. I think so. This is enable. Yep. Then we also doing the interrupt, making space, interrupts, EICRA. This is on page number 54. External interrupt register A, and we start with a minus. Nothing inside. Bit number 6 is a minus, and bit number bit number 5, it's also a minus, and bit number 4, it's a minus. I found it out very funny in case of that. What does that mean? Yeah, and 5 is a minus, and 4. And now it's coming 3. ESC 11 is the 3. ESC 10 is the 2. ESC 00 it's the 0. This is interesting. What is gonna happen now? 3, 2. No. This is 3. This is 2. This is 1. And the ES 00 is the 0. So now it's correct. And that means 1 1, the rising edge of int 1 generates a interrupt request. Okay. And now we're doing what? It's very simple. It's equal int 0 a1 rise edge is OB for binary, 4 zeros and 4 ones. And this is an external interrupt. Null rise edge int 1 rise edge. That we need for the future use, and it's also we need also page 55. And here we have this. This is an equation. Interrupt 0 a1 IMSC. It's a mask. It's 0b 8 2 4 5 6 7 8. There is one too much. And this is an external. What does that mean? This is an external enable. This is int 1 external enable. Is the external interrupt for the future use. What we need after this program, but we write it now. It's one time written in your life. You never use this again. You write it only one time. It's these are the interrupts for the turn push and enable external int 1 and int 2. These are for the interrupts. Yes. Interrupts are things that you have from extern, like input for a switch or for a rotary, where we aligned in future user interface also. Yeah, this also we built in now in this grid. We have here the PCECR. This is on page number 56, and that makes other pins to change the interrupt control register. You have that for that you can align, for example, pin number 20 to an interrupt, to an external interrupt, and so we do that. This is very important for us. We do that first. So we're making an equation. PC int 0 ENA, that means enable. We enable this by the 0 bin. 1, 2, 3, 4, 5, 6, 7, and a 1, 2, 4, 6, 8. Okay, it's 8. And this is the control pins number 2 and PC interrupt enable number 1 and PC interrupt enable number 0. PC SK0. Okay, this is in this register, and then we also having a second. This is PC interrupt 20 ENA enable. We do that here. We use this bit, yeah, and PCIe 2, and we have this PCMSK2, and we have this PCIe 1 here, 1. These are control bits, PCIe 0, okay. And then we need the change mask register. This is the PCMSK2, page number 57. This is pin change mask register. And what we're gonna do with this, we have there a lot of things to do. It's equal PC interrupt 0 PCM SK0. This is a mask register. Is 0B, and where is the mask? Aha, it's on the first pin, on the first bit. And there are PC int 7, pin number 7, and so on. PC int 0 at 0. Yeah, you can see it here. This is on the mask. And also we would like to do that on the second mask. PCMSK. There you orientate the mask what are opening and what not opening is. That means page number 57. This is also the same pin change mask. Register for the interrupts for the external. And we're doing the same, but this is PC int 20, PCMSK 20. This is the 20 mask, and it is 0B 1, 2, 3, 1, 2, 3, 4. Okay, and these are the masks for the PC interrupt number 23. Pin 7 till PC interrupt 16 bit 0. You can see it's on 20. Here is the 16, here is the 17, 18, 19, 20, and the 20 is the mask for that we used. So now we store that. And we are gonna say here start the program. Here start the program, and after reset the program counter, is on address 0. We have a 16-bit address. The 16-bit address, you see? And here the program is starting. We have here address, and this address will be org. We org the address, and this is address. Here is the program counter address. Okay. We org it here, and we say we stay start, and we say here start. And now we're writing the first label. This is a label, yeah. This is an address level. This is an address. Oh, too much R. Address level. Or this is a level on address. Okay. This is a level. A level is with a other. Okay. You see that this is a address level. What we're gonna do first, we jump to the program start, to the initialization, and this is a command. We go with the tabulator in, and we say rjump to the reset vector. Okay, to the reset vector. This command jump to the level with the name reset vector. Okay, and we do the classical. Here are the interrupt vectors. This is only information for you. And here is the start. Here is the initialization of the program. And here we writing reset vector double point. This is a label, and at the reset vector we are doing this following. We must do one very important thing. There are some vectors inside the RAM, inside the controller, and there is one vector. This is the stack vector, yeah, and the stack is following. We talk about later about the stack when we use it. It's a stack for storing the data and also on it, and we are doing this, but this is later. And now we change this. We say the following. LDA means load immediate, and now we're using the temporary register. We load the temporary register with the high byte of RAM end. And vector. What we're gonna do, we put it on stack pointer high temporary register. also during the setup we taking to the temporary the low RAM, and this is load the low byte we have only from the RAM end vector, and we put it there. Out SPL temporary. We put it in the stack pointer low. Okay. This is very important. Never forget this to do. Now we are initializing the board init. We say board init as remark, and we say init underline board as the level. And what we gonna do? The first we load immediate temporary with init port B, sorry, DDRB. This is the data direction register, and we give it out it to DDRB temporary. We load the init of DDRB to temp, and give it out to the register for DDRB. Data direction register. Okay. Port B. So, and then we would like to also do the same with the pins outside the board B, and we initialize the board pins outside the board B. Load immediate temporary with init board B, and we say out board B with temporary. We cannot write direct. This is not possible to write direct with a number to the external board. You can switch a pin, but not a port. Complete. Load the init of port B to temp. This is a value, not the init value. Value. And now give it out to the register for port B. So these are the bits outside for the port B. So now we're doing the port B, and now we're doing the port C. Load immediate temporary init DDRC, and say out DDRC with temporary, and say load immediate temporary init port C. These are the things what you're gonna do first in the up in the definitions. Now we do that with the port C, and we say it out port C temporary, and we do the next and the next. It's very easy to understand. We do the port B, the port C, and the port D. Load immediate temporary with init DDRD, out DDRD with temporary, and load immediate temporary init underline port C, and out port C with temporary. Okay, it's all the same. Now we initializing the port. Then we go into our status register and load immediate temporary null into temporary. Okay, load immediate load immediate into the temporary and move it to the status. Inside we move, yeah. And the thing is that if you move from temporary status, if you move from temporary to the status, it's internal. Temporary is register 14 and status is 19, or what it was. It was up here. You can see we have here status is you move from R16 to R20, and then we have zeros inside. That means we are signaling with high, or should we signal with low? I don't know. Is that good or not? Should we set a bit or should we clear it? Normally clear it, and we can say FF. We say FF load immediate, FF into temporary. We let it be. The flags are coming and it's positive. It's positive. So what we're gonna do now? We are installing the timer 2, and this is here. The timer 2. We say load immediate temporary. Now we have Tim2 that we count, and we store it. It's in a RAM position. We store the TCNT2 in temporary. This is a timer counter 2. Start position, and this is the start position. I think so, 0, it was so, yeah. Then we gonna do and say load immediate temporary, temporary with what? With the Tim2 VGM21, and here we say counter is null. Counter is null. Yeah. We can leave it so, yeah, okay. And we store it normal inside the controller. Store this in, and this is a VGM21. It's bit 1, page number 127, I remember. And then we going to load immediate temporary. We use also the same temporary. We override it time. Tim2 underline OCR2A underline comp 2004, and this is the OCRA2A max count 10 milliseconds. You remember that was so complicated to understand STS with the cycles to A and this temporary. Yes, we do that. As we do that, and then we are starting the things. Load immediate temporary with Team2 CTC CS 2024. This is the command. Prescaler mode. And then we must give it to the TCCR2B, the temporary. That's correct. Load immediate temporary. We're doing the interrupt. Start to. What's here? Here is something wrong. These are to be temporary too. So in this start, it's not good. This start counter clock by divided by 210. Okay. Here we load the temporary with the Team2, and we say the OCIA2A. This is the interrupt enable. Enable command, interrupt, enable command. And we stored it in the TIMSC2 in temporary. This is the enable command interrupt. This is the OCIA interrupt enable 2A. Okay. Then we interrupt. We enable also the sleep. The sleep is also good. We load immediate the temporary with the sleep command. It's idle mode enable. We say sleep enable. We say sleep enable, and this is also important. We say out. And here we must say out. Under the address of the RAM, we must say out. There are registers like the timer 2. They are outside of the internal register structure, and we must say to them out. And the other registers, they over them, we must say store as. Yes, this is one complicated thing. SMCR by the temporary, and this is the sleep enable. And then we're writing set double point, and we jump to the set. That means sleep, but in future we say sleep. This is only this jump forever to Z means sleep. This is only for the simulation. In case of that the AVR Studio cannot, AVR Studio cannot make the sleep sometimes and sometimes not. I don't remember what's happened with this. And it's complicated to do. So, what happened now? We must go back, restore. We must go back and we insert one very important thing. Here we go to the interrupt vectors. What are the interrupt vectors? After these 10 milliseconds are running over, now we installing the complete system, and after these 10 milliseconds running over, an interrupt occurs. And what happened with it? This is a very complicated thing. Yes. This we go here and we say here, we orged it to 100. Not standing in the room. That means it fixed at 100. Yeah. And here we also go here. We say interrupt vectors. We say it's. We say what? We say org. OE. OE. We can say here blinky. Say here blinky. This is only information for the if the interrupt comes, it jumps here to this address. This is an interrupt vector, and this interrupt vector, we would like to say it should jump to the TIM2 comp A handler. (10 milliseconds). It come here. Yeah, this interrupt vector, and all the 10 milliseconds it come here, jump to here, and then we jump to this interrupt handler. Yeah, sorry, jump to this interrupt handler. What does that mean? This is very, very interesting. And this interrupt handler, we put it here. We say here, here is the interrupt handler list. And we say here this level, TIM2, it jumps from here, TIM2, comp A, underline handler. This is a level. It jumps from here, the interrupt brings it here and read this command and jumps to here. Correct? And then we say clear bit immediate, port C, bit OSC. Bit OSC, I think it was 5. Bit OSC 5 is now low. Falling edge. Then one important thing, we do nothing. and then not meet no operation. Only the time is gone. 125 nanoseconds plus. All these steps is 125 nanoseconds. And now we say SPI port C, set bit in port C, bit OST C. What's happened with this? The bit OST C, number 5, is now high, rising edge. Okay, then we're doing a level that's called like control, and here inside this level we have a ARCO subroutine. There are all programs are coming. Here are all sub programs are coming in. And then return interrupt. So that's finished. More cannot be. We must store it, and then we go into the Windows computer and assemble it, because on this computer I don't understand how to assemble the program. There is a program, but no way. And now I have found out also I forgot this to enter. One of the important thing is SI. This is the global interrupt enable. This we should have also, that this program will run and store on the base grid. That was the first grid written in assembly for the ATMega328P. And this is the important grid what you need in your life. Yeah. I don't give it as copy free, you must write it yourself. This is very important that you write this, so you are familiar then after this writing with the registers inside this controller. And I show you in the next video how we assemble this on a Windows computer, and we measure it with the oscilloscope that the signal came out with this 10 milliseconds. You say, for what this much work is? You can make a blinky with a wait. Wait is illegal. It's an illegal. It's an illegal command situation for a controller. Nobody wants wait in the lifetime. That must be run over timers, over interrupts, and with a sleep. This is the important thing what we need, and we go this correct way. The controller never worked. It worked only if something is happened, like the overflow from the 10 milliseconds timer, or a blinky LED, or LCD update, or knob for the input for the user interface. And the controller is sleeping the whole time, or idling. If you like my channel, please subscribe, and thank you for watching.